So let's now analyze the scattering from a Thomson atom. Now, if I think again about my target, as we had just been saying, we can analyze one atom at a time. That really simplifies our analysis. And the other thing I'd like to do to simplify our analysis, and this is a very important thing if you're going to take a theoretical approach to anything, the first thing you want to do is begin with a rough order of magnitude analysis, right? I just first want to see if the theoretical model that I have in mind even has a chance of explaining the experimental data, because I can carry out such an analysis very quickly. And if the order of magnitudes don't even line up, then that can save me a tremendous amount of wasted time in doing a detailed analysis of a theory that is just not going to work. So you always want to begin with that order of magnitude approach before diving into the detailed analysis. Okay, so just thinking about orders of magnitude now, I want to see how much scattering I can expect from a Thomson atom. So here again, here's my target, right? I have my Thomson atom. It's this large, positive sphere of positive charge of a given radius. And I should point out that now, because we know the masses of the individual atoms, and we know things like the density of materials, we now knew how much space the atoms take up. That's another consequence of Millikan's beautiful measurement. And that radius, it turns out to be, is on the order of, it's usually a little bit larger, but it's on the order of about 1 angstrom, which is 0.1 nanometers, or 10 to the minus 10th meters. Okay, now, within this Thomson atom, all right, I've got gold, so I've got 79 electrons in here somehow, right? That's quite a few electrons. We don't know exactly how they are going to organize themselves, right? But this is just order of magnitude analysis. But we can be pretty sure they hate each other and going to avoid each other, and that they will arrange themselves in some sort of a symmetric pattern, because this whole model is spherically symmetric. So we might imagine there's sort of like an outer shell out here where the electrons tend to distribute themselves, like so, perhaps, right? Something like this is a reasonable model. Now, let's consider what happens when alpha particles travel through here. So if I have an alpha particle, maybe who's going to start up here, and he's approaching my target, right? As he now moves outside of this distribution, what I want you to notice is I basically have here a solid sphere of charge, positive charge. And then I have a shell of negative charge whose charge exactly balances the charge in the positive charge. And you guys know from your electrostatics and Gauss's law, when you have a spherical neutral distribution, once you get outside that distribution, the electric field is zero. So even though this alpha particle is approaching with a total charge of plus 2e, right, it's not going to feel any forces from this Thomson atom. It's just going to sail straight on through with no scattering. Okay, that's one extreme case. I always like to think about the extreme cases first. The second sort of extreme case is, well, what happens if I send someone here dead on to approach my atom? So I'm going to send them in here like so, right down through the center of the atom. Now, in this case, right, if I think about the electric fields involved, there's as much positive charge above me as below me, right? And my point, I guess, is first I've gotten through this outer electron shell. So now I actually can feel the very strong positive charge of my nucleus. But because I happen to have been going straight down the central line, right, by symmetry, I've got as much positive charge above me as I have positive charge below me, so I'm going to be heading, straight on through here. Again, I'm going to have zero scattering. So really, again, just from order of magnitude type of an approach, the strongest scattering I can expect, I would say, would be somewhere, about halfway between these two extremes. So here would be an alpha particle that's going to come in, right, I was trying to draw him straight on in. My diagram is a little off here, so maybe I'll start him down here so I don't get too messy, right? And I'm coming along, but just imagine that's about halfway up, right? What will happen is I will get through that electron sphere. I will then begin to experience the very strong positive charges from the inside. I'll be repelled from the center. I'm going to begin arcing, right? And I will then emerge with some kind of significant final scattering angle theta. And that's the type of thing that I want to calculate, or I want to imagine calculating. Now, before I get into that estimate, I do want to clear up just one thing. And this is kind of very important in the analysis. You might think, well, wait a minute. Why am I actually allowing these nuclei to interpenetrate each other? Right? Am I supposed to think really of these as hard spheres? Well, one thing that very quickly rules out the hard sphere possibility is the fact that I do not have multiple scattering events, as we had just discussed. If I really had spheres, right, that filled up the spaces between all of the atoms, if I had a dense set of spheres like that were essentially closed packed in the material, they'd be packed in a way kind of like when you stack, you see the oranges or the grapefruits stacked at Wegmans, right? After just one or two layers of stacking them this way, there is no way you can get through this system, right, directly without scattering off of multiple atoms, right? So we know it can't be a situation like this. So we can rule this out already, that we are hitting some kind of hard spheres. Now, it's also possible, right, to imagine that, well, maybe they are hard spheres, but they're very tiny hard spheres, so that there's a lot of room for the beam to actually come down and penetrate in the cracks between here. And that's a reasonable thing to think about. And in fact, that you can calculate the scattering cross-section just the way that I'm doing here for such small-ish sized hard spheres. When you do that, what you actually end up with is a constant scattering at all angles, which is also a direct contradiction of this very strongly decaying function that I'm showing you here. That even though it strongly decays, it still picks up quite a large significant angles. So we can rule out this possibility here as well. So the idea of these atoms as being hard spheres in collisions, we can dispense with. What we're left with then is this idea that, yeah, I might be able to actually travel, the nuclei may actually be able to overlap with each other, and so that's the type of effect I'm trying to calculate for you here. Okay, so with that said, let's try to put an order of magnitude of how much scattering I could expect at maximum from such a collision. So this is going to, and in particular, I want to calculate the tangent of the maximum angle that I might expect. And the reason why I like the tangent actually is that this estimate, as you're about to see, is going to follow very closely the analysis that we had done some time ago, actually, when we looked at the angle of scattering, right, from the J.J. Thomson experiment. Basically, again, I'm going to have a momentum conservation type of an argument. So the idea would go here, roughly speaking, something like this, right? I'm coming in with some rather large parallel momentum, which is the mass of my alpha particle over here times the velocity. And I know actually this velocity because I know their kinetic energy, again, is 5 million electron volts is kinetic energy, capital T. So I can figure out this incoming parallel momentum. And again, this is just order of magnitude estimate. I'm going to be deflected then by the positive charge on this Thomson atom. And that deflection then is some perpendicular momentum that I'm picking up. And what I pick up then comes from, again, order of magnitude estimate, the average force that I'm feeling while I'm in there times the amount of time that I actually spend in there. Now, in terms of that amount of time, We really are just trying to do order of magnitude estimates here. You can see I'm traveling with a certain velocity v. It's very much like the Thomson analysis, and I'm passing through a certain distance of this atom. It's not the full diameter. It's not 0. Somewhere halfway between those would make a reasonable estimate. So I'm going to think I'm going to travel, say, a distance roughly r is the distance I travel through this atom. So the time it will take me for that, again, order of magnitude, factor of 2 type estimate will be distance traveled r divided by, say, my velocity. Now the force. Now for force, this alpha particle is feeling some type of an electric field as he travels through here. And force is charge, and in this case the charge is plus 2e, right, times the electric field. And once I get inside this negative electron shell, I'm going to be feeling, the full charge of this nucleus. And in fact, I'm trying to make an estimate of the maximum angle of deflection. So we may as well use the maximum possible Coulomb force we can imagine. So let's just ignore these electrons, which might tend to cancel some of that force, right? And focus on the force from this charged sphere. And now you guys know how the electric field works, I think, for a charged solid constant charge density. You might remember the electric field is 0 in the center by symmetry, and then it grows as I approach the surface. Outside the surface, it just takes on the point charge value as though the entire sphere were concentrated on its center. And as I go from the center to the outside surface, it just varies linearly. So I'm going to say maybe the typical electric field strength I'm feeling in here is something like the full electric field I would expect from the total charge that I have, which is a plus 79e is my charge. You have to multiply, of course, by Coulomb's constant, Kc, right? And we have to divide by then the distance. Now remember, our argument is that the force in here is varying linearly between 0 and the maximum force, which is when you're outside. And when you're outside, you just feel it as though it were a point charge. And if I'm right on the surface, it's a point charge at the radius of my sphere. And that radius is some capital R, about 1 angstrom, so R squared. That's the maximum electric field I would feel right at my surface before it begins to decay as I'm traveling away. But as we were saying, we seem to be scattering here about halfway up. So, and the field varies linearly with distance from the center. So I'm going to put in another factor of 1/2 here just to try to be somewhat accurate. Again, it doesn't matter that much. I just want to get order of magnitude here. Great. So now I've got my force determined that I can stick in for the force. I had a determination for the time spent. That gives me perpendicular momentum. I can divide by parallel momentum and estimate then my angle. So P perp over P parallel. My P perpendicular then. Here I've got all of these factors here on top. And then I divide by mv. So it's going to be some kind of a big fraction. Let's just try to track all of our factors. First, we have our numerical factors to think about. Well, here's a factor of 2, cancels this with this half. And then I'm just left with a numerical factor of 80 up here. So let's put 80. The rest of what I have on top, oh, look, there's some more canceling when I multiply f times delta t, right? This radius up here cancels one of the radii down below. And then finally, what I'm left with, if you're very careful, there's Coulomb's constant. I've got 2 electron charges, and then divide by the radius of the atom. So there's Coulomb's constant E squared over the radius of the atom. Those are all the factors coming from up here. I've got one more factor, divide by V, and then that whole thing is divided by mv. So I've got mv squared on the bottom. So this is sort of my order of magnitude estimate of the most scattering I could expect out of this situation. Now, we have to try to put some numbers on these things. And there's a few things we can do here. The first thing is the bottom looks a lot like a kinetic energy. So let's multiply top and bottom by 1/2 to keep things the same. But now this 1/2 mv squared, I know its value. That value is going to be the kinetic energy, which is 5 million electron volts. So that's 5 MeV there. Now, I've got a numerical factor here, which of course is just going to give me 40. And what it's multiplying is this interesting combination. Coulomb's constant, which we know, the charge on the electron, which we now know, and a radius, right, that we know for the atom, for this Thomson model of the atom at least, is about an angstrom. And in fact, to be just a little bit more realistic, I'll put in maybe about 1.5 angstroms. And the reason why I'm doing that is actually then I know that this combination on top has a very specific value, which turns out to be, if you run these numbers, and later on in the course you'll see why I know this right off the top of my head, this is going to be about 10 electron volts. So at the end of the day, now we have an interesting ratio. We have 400, right? 40 here times my 10. So I've got 400 electron volts on top, and I've got 5 million, so 5 times 10 to the 6th electron volts on the bottom. Oh, that's going to be pretty small, right? So I've got about 4/5, which is of course 0.8, and then I've got 100 divided by 1 million, or 10 to the 2 over 10 to the 6th. That gives me 10 to the minus 4. So this whole thing is an angle of about 8 times 10 to the minus 5 radii. That's my tangent. It's tiny, right? We had said, and that's our estimate of the maximum scattering we could expect in this situation. And we had said, in fact, that we were thinking instead, right, that we should be able to get, when we look at our observations, right, angles whose tangent even is 1 are not completely uncommon. And we're finding a maximum scattering that is way too small. So this is a major fail for this model. Far too small. So we don't even have to do a more detailed calculation of, scattering through constant charge densities, or even trying to figure out exactly how the electrons are arranged. It's just, with this type of electrostatic interaction, there is no way you're going to get that observed amount of scattering. Now, it's not a total loss, however. Let's think about this just a little bit. Right? We can adjust our model. We clearly are going to have to adjust this model. And one of the ways we can think about adjusting our model is to take a look at our final calculation. We needed this theta max, really, to come out where its tangent was more like order 1, not 8 times 10 to the minus 5. So we should look in here to see what parameters are under our control that we can adjust. Right? Well, we can't control Coulomb's constant or the electron charge, right? We can't, in our model, adjust those. We can't adjust the incoming kinetic energy of the alpha particle. That's fixed in the experiment. The only parameter, really, that we could imagine mucking with here is this somewhat arbitrary choice of r, right? This represented the radius of the positive portion of my atom. And if I want to get this thing to be much, much larger by a factor of like 10 to the 5, what that means is I need to get this radius here to be much, much smaller by about that same ratio. That is the only way I can get strong enough forces to explain the type of scattering events that I see. So let's just note this down. It will work if we reduce r by a factor of 10 to the 5th, meaning we're going to say that r now is about 10 to the minus 15th meters, or about what's known as 1 femtometer. Now, that means what we have, instead of a Thomson model for the atom, we have this Rutherford nuclear model. This leads us to a nuclear model. In the nuclear model for the atom, because nucleus really means center, the idea is all of this positive charge is concentrated in a very tiny center, which actually turns out to be about exactly this size. And all of that charge Q equals plus ZE is concentrated there. And the electrons then must be somehow outside of this thing to give it its size, moving around in different orbits here. I'm trying to draw some like orbits for my electrons. You've seen the typical atom picture with electrons going around in, all kinds of different crazy orbits. That is the model that we see, where now the radii of these orbits has to be correspond to the size of the atoms, about 10 to the minus 10 meters, whereas the nuclear size is much, much smaller. This is about 10 to the minus 15 meters. So we find, in fact, that the atom is mostly, and you've probably heard this before, but this is how we know it's true, is mostly empty space. And this tight concentration of charge at the center, this is what we call the, I'll give it a radius lowercase r because it's much smaller. This is what we call the nucleus. And this is our second component that makes up the material world around us. So really what we want to begin to think about next is, now that we have a much better model, we're going to think about the interactions. But before that, I just want to leave you with one final comment, and this is why we had that interesting theoretical paper from Rutherford. The final comment I want to make is that if we assume this point charge nucleus, I mean, it's really so tiny that the alpha particles have very low chance of hitting it. They do every once in a while, and you'll get an extremely strong scattering event. But most of the time, because this is such a small cross-section, you almost never make direct contact with it. And once you're outside that nucleus, of course, we can treat it as a point charge. If we assume a nuclear point charge, you can actually calculate the scattering cross-section. And you get this prediction that the number at each angle theta, in fact, should turn out to be exactly what is observed, sine to the fourth of theta over 2. And that can't be coming from a coincidence. So that's really the direct evidence for the nucleus. Very good. So now we have our two basic components of matter.